So, and remember, what is the response to e to the j 2 pi f t? It was nothing but integral 0 to infinity h of t comma tau e to the minus j 2 pi f t f tau theta, right, this times e to the j 2 pi f t. So, this is the frequency response, this is nothing but h of j 2 pi f comma t, correct. All right. Now, h of t plus Ts comma tau is the same as h of t comma tau. What does that mean? As far as h of j 2 pi f comma t is concerned, what should you expect? What did we say before we started through all this math? The gain experienced by a sinusoid at f should be, the system is varying periodically with with a period Ts, correct. So, what should you expect for the gain experienced by a sinusoid at f? Yes, it should also be periodic. So, now can you use that to basically stare at the expression for h of j 2 pi f comma t and figure out whether it is periodic? You simply replace h, okay, well, h of j 2 pi f t plus Ts is nothing but integral 0 to infinity h of t plus Ts comma tau e to the minus j 2 pi f tau d tau, correct. And lo and behold, this is the same as h of t comma tau, correct. So, this is therefore the same as h of j 2 pi f comma t, right. So, in English, all that this means is that is the same as h of j 2 pi f t plus Ts. All right. So, I mean, this makes intuitive sense. I mean, forget about all the math, but you should be able to intuitively see why this makes sense, because the properties of the system are varying periodically. So, you expect that the gain experienced by the sinusoid, right, will also vary periodically, correct. So, the output waveform will therefore look like this. So, this I think we have already seen, right. All right. So, the resistance is varying periodically, right, and in this fashion, and as you can see, the output waveform is also it kind of looks like this, where the envelope is changing periodically. One question I would like to ask you is, the gain is changing periodically. Can you comment on the output being, so you put in e to the j 2 pi f t into the LPTV system. The output is h of j 2 pi f comma t times e to the j 2 pi f t. This is periodic with a frequency Fs, which is 1 over Ts, right. Can you comment on the periodicity of this waveform? What is periodic here? What is periodic on the right hand side? Is the whole right hand side periodic, or I mean, we have no control over what the input frequency is, man, right? What all are periodic? I mean, this clearly is periodic with frequency 1 over f, I mean with frequency f, sorry, and h of j 2 pi f comma t, this is periodic with fs, which is equal to 1 over ts, correct? And but what comment can we make about this waveform? I mean, unless f is related to fs in some special way, right? In general, the waveform on the right is not, please don't get be under the mistaken impression that the waveform at the output is going to be periodic. The output waveform is not going to be periodic, it is only the gain experienced by the sinusoid which is going to be periodic. Does it make sense? There is a difference between the two. Do you understand? Right? And here is an example, right? I don't know, I think it's visually obvious that this waveform, though it's tempting to think it's periodic, it's definitely with this is the period Ts, right? And clearly this is not periodic. This is the output waveform, and as you can see, the output waveform is definitely not periodic. But how do you find the gain now? What would you do to find the gain? In other words, how would we find the gain experienced by the sinusoid? We have the LPTV system. How would we find what the gain experienced by the sinusoid is? Pardon? Yeah, so basically cos 2 pi ft, and then the same LPTV system you excite it with sin 2 pi ft, and then you get Wi of t, Wq of t. Can you comment on the periodicity of Wi of t and Wq of t? They will not necessarily be periodic. I mean, unless that input f is chosen to be, I mean, if f happens to be also fs, for instance, that's one case, or nfs, then then you can expect the output to be periodic. But otherwise, in general, Wi and Wq will not be periodic. So what will you do? I mean, to find h of j 2 pi f comma t is same old. It's Wi plus j Wq times e to the minus j 2 pi f. Is that clear? And now, is this periodic or not? This is that h of j 2 pi f comma t, and this is periodic with fs. I mean, you understand what I am saying? You understand, right? All right. So, sure enough, I mean, here is an example. This waveform is clearly not periodic, right? That guy there, that's the output of the capacitor, voltage across the capacitor. But if you look at the real part and the imaginary part of magnitude and phase, you can see that this is definitely periodic with a period equal to Ts. Very good. So, now let us see what this means. I mean, whenever we see, we are electrical engineers, so whenever we see something periodic, what do we like to do? Well, that is the only thing we know how to do, which is expand this in a Fourier series. right. So, well, how will you express this as a Fourier series? Sum over k, right. This is periodic with respect to which variable? It is periodic with respect to the time variable, with respect to the time variable. So, what will be the, there will be some a sub k, which is the Fourier series coefficient of the kth harmonic, and the kth harmonic is basically e to the j 2 pi. The fundamental frequency is Fs. So, this will be e to the power k times Fs times t, correct. And well, what is Ak? How will we find Ak? It is 1 over Ts integral h of j 2 pi f comma t e to the minus j 2 pi k f s times t dt from 0 to Ts, correct. And this is going to be therefore a function of, well, if you integrated out time, what is left? This is h sub k, right, of some j 2 pi f. This is exactly like your regular Fourier series. I mean, except that you know that there is another. I mean, there is the it depends on f. That's all. I mean, intuitively, what's happening is that if you put in a frequency f, the sinusoid experiences some gain. The gain experience is periodic with Fs, correct? All right. Now, if you change the input frequency, what do you expect? You expect that the gain will change, but that new gain will also be periodic with Fs, right? And therefore, when you change f, the Fourier coefficients of that periodic gain function will change, correct? So, that's all that this math is saying, that this Ak, the Fourier series coefficient, happens to be a function of f. That's all, right? So, instead of writing Ak, to remind ourselves, we basically express this as h sub k of j 2 pi f e to the j 2 pi k f s times t, right. So, the fundamental frequency of the expansion is Fs, and so I am going to write this as hk of j 2 pi f is this, all right. In English, all that it means is that we saw this picture, remember. Well, you know, imagine, I mean, this is a complex, I mean, if you combine the ray angle and the magnitude, you will basically get a complex waveform which is periodic with time. You are expanding that complex waveform in a Fourier series, that is all, correct. And therefore, you will you know, you will see, you will get a Fourier series expansion, and right. When you had a real waveform, what did we, I mean, what constraint does that impose on the Fourier series coefficients? Conjugate symmetry. So, Ak would be A minus k star, but here what comment can we make? This is not real anymore. This is a complex waveform. So, when you expand this in a Fourier series, I mean, should we expect h is, we are used to seeing hk of j 2 pi f being equal to h minus k of, is this correct? This is simply conjugate symmetry of the Fourier series coefficients. So, the question I am asking you is, in all the stuff that you looked at till now, you probably have, have this happen automatically, because you're trying to deal with the expansions of real waveforms. Now, what comment can we make? Is this true? Yeah, so on the left hand side, you have a complex number, right? A complex waveform, so and therefore conjugate symmetry is not necessarily okay. Can you give me an example where it is actually true? Can you think of an LPTV system where this is actually true? Pardon? Memoryless system. For example, if you have the very first thing here, what is the gain experienced by the complex sinusoid? It is simply a cos 2 pi ft, which happens to be, that gain happens to be, it's supposed to be, I mean in general it is complex, but in this particular special case it happens to be real. It's only in that case will this hold. Okay. However, remember that h of j 2 pi f comma t must be the same as h of h star of, what is h of j 2 pi f comma t? It is nothing but integral 0 to infinity h of t comma tau e to the minus j 2 pi f tau d tau. So, h of minus j 2 pi f comma t is simply, we have seen this before, right, j 2 pi f tau d tau, which is S Karthi, h star of j 2 pi f comma t, correct? All right. Now, we saw this, we have seen this already. What does this mean if h of minus j 2 pi f is h star of j 2 pi f comma t? What comment does it I mean, what does that augur for the h sub k? What does this say? What does this impose? What constraints does that impose on h sub k? H of minus j 2 pi f comma t, therefore, is simply h k of minus j 2 pi f e to the j 2 pi f s times t, okay, and h minus j 2 pi f must be the same as h star. What is h star? Is, pardon? So, h star is this, correct? And now, can you stare at these two and tell me how they must be related? So, h k of j 2 pi f must be equal to h minus k star of j2 pi f or minus j2 pi f? Minus j2. All right. Okay. So, all right. So, the next thing to note is the following. So, we excite the system with e to the j 2 pi f t, out comes e to the j 2 pi f t times a complex gain which is varying periodically with time. So, that that we know can be expanded into h k j 2 pi f e to the j 2 pi k what? Fs times t, correct, which is equivalent to saying that this is nothing but k h sub k j 2 pi f e to the j 2 pi into f plus k f s times t. All right. Sanity check. I mean, well, a linear time invariant system is a special case of a linear time varying system. It is a special case of a linear periodically time varying system, correct, where the gain happens to be constant with time. So, if the gain is constant with time, what comment can you make about the Fourier coefficients? Which of those Fourier coefficients will be? Only the DC component will remain. So, that basically LTI system h sub k of j 2 pi f equals 0 for k not equal to 0, right, and therefore, if you put in e to the j 2 pi f t, you only get h 0 of j 2 pi f times e to the j 2 pi f t, correct. We knew this, of course. I mean, there is nothing new about this one. All right. So, the key point is that in an LTI system, when you put in f, a frequency f, at the output you only see the same frequency f, right. Turning this upside down, at the output of an LTI system, if you saw a frequency f, it must mean that the input must also have been at the same frequency f, right. You knew this, of course. Now, in an LPTV system, the input is at f. What comment can we make about the output frequencies in general? So, the input frequency is f. In an LPTV system, in general, you will see output frequencies, you will see tones in the output at frequencies f, f plus fs, f plus 2fs, f minus fs. So, you will see all frequencies of the form f plus k times fs, where k is an integer. Does it make sense? All right.